The speaker today is Marek Lewicki from our institute. And the title of this talk is Search for Cosmological Phase Transitions through the New Gravitational Wave Signals. Well,
thank you. All right. Yes, it's showing up. I see. Okay, perfect. So thank you very much for the invitation to give this talk. So indeed, the title is Search for Cosmological Phase Transitions through the Gravitational Wave Signals. In the first part of the talk, I will definitely focus on the search part, and only towards the very end, a few words about gravitational wave signals from phase transitions. So to start off, a bit of an overview of the field of, let's say, searches for gravitational waves. Of course, the starting point is LIGO. I'm sure I don't really have to introduce to you what it is. It's a collaboration which currently has 4 interferometers. Arm length is 4 kilometers, at least for the LIGO sites. And then, of course, what it does is measure the relative change in the length of the arms. That way, looking for gravitational wave signals. Of course, it does so with great precision. And as I'm sure you know, it has discovered gravitational waves. So this was the big breakthrough. I keep saying it's recent, but I realized making this talk that it's been almost 10 years now. And since then, of course, the field was rapidly growing. LIGO keeps on observing more and more signals of this sort, so collision of astrophysical objects. This is not very up-to-date data, but you can see that there are a lot of collisions already discovered. Of course, I'm told that LIGO is taking data now, and this will keep on increasing with time as the experiment continues to operate. Now, what I will be talking about and mostly focusing on is early universe sources, which sadly LIGO has not seen a signal which would correspond to that, which would look quite different than a transient, very loud and relatively short-lived signal from a collision of 2 black holes. So most of the information that we have on the universe, on the early universe, comes from light-based sources, as you know, cosmic microwave background. So these are photons that were around 307 when the universe was 378,000 years old. And when the temperature dropped enough that the universe, well, ceased to be opaque because electrons found nuclei and produced electrically neutral atoms, they started to propagate freely. This is why, not interacting with anything up until we are able to see them today. So we essentially see a map of the sky from, well, back in that time of the evolution of the universe. However, the problem with light-based sources, of course, that the universe was opaque before that. So any possible source before that would not leave a signal in terms of photons. And this is why gravitational waves are so important, because luckily, if produced even much earlier than that, they decouple immediately. They don't really interact with anything up until we can measure them today. So we can look much further back in time. And this, of course, also tells us that for those sources, what we expect to see is something not unlike the CMB, in the sense that it's a stochastic background. The horizon was much smaller at the time. So, of course, well, before it will be even smaller than at the time of the CMB. So looking in the sky, we will always see a large ensemble of areas that were in contact back then. So we're not really interested in any individual realization, but rather statistical properties of the source. And what we will see is, again, a map, which will come down to a certain spectrum of gravitational waves. So what I'm showing here is the currently operating experiments in terms of the variables of energy per decade of frequency. If integrated, that will just be the abundance of gravitational waves today. So first, of course, we have LIGO, which I already said a few words about. Sadly, as I said, it didn't discover a stochastic background just yet. So for us, this is actually an upper bound, but it will continue on taking data. So who knows, maybe we will see something in the future. And then the second very interesting thing that is in this slide is nanograv. But please let me pause the explanation of what that is to a bit later, because when I finally do, we will just stick with it till the end of the talk. So before we do that, let me just say that there are two ways of detection that are currently operational. Both of them are finding extremely interesting data already. So it's no wonder that the field is expanding quickly, and there are many more experiments planned in the future. So I would like to say a few words about a few of them, because as you see, the prospects look very bright. We will cover a whole lot more of this parameter space, which is of interest to us. So, well, let's go through them briefly. Firstly, of course, there is the Einstein telescope. I'm sure you know what that is. I'm sure it was introduced in one of the previous seminars in this series. But this is essentially a next generation device operating on a similar, operating in a similar way than LIGO does, but of course with many improvements, so much better sensitivity. I'm focusing on the European project. This is the Einstein telescope. There are different ones, but this is, well, at least with this one, I know there is a big collaboration behind it, which is very active. So it's rather a question of when the detector will be made rather than if, it seems. But as far as I know, it's not fully funded. So, and the last answer to the previous question I made was maybe 2040. So this is what I put on the slide. But anyway, it's coming, so we will have access to that part of the parameter space. Then going to lower frequencies, which essentially means we need a longer arm of our interferometer. We have to launch into space. So this is LISA, a laser interferometer space antenna, which is a triangular configuration. It's again an interferometer, so the satellite exchange laser beams. And our arm is indeed longer, 2.5 million kilometers, which puts us at a frequency of about millihertz. And here the situation is even better. Luckily, the experiment was already approved and adopted by the European Space Agency. So it is in the phase of commissioning. Currently, the consortium is reforming following the implementation last year, but the current planned launch is 2037. So if everything according to schedule, it goes according to schedule, we will have again access to a lot more new data. Perhaps I should say that I am currently one of the chairs coordinating the cosmology working group within the consortium that is working on the analysis for LISA. So if any of you would like to join or have some ideas, please feel free to talk to me and I'll do what I can to help. Yes.
So in this space, how does it exactly supposed to work? Because on Earth, I more or less know that they measure the change of distance when the gravitational wave goes in some direction that is normal and closer, let's say. But in the space, what's the mechanism? I suppose that controlling distances between the
spacecraft, yes. No, it's not. It's supposed to be relatively stable. This is so the idea behind the method of operation is pretty much exactly the same. There was even a pathfinder, which was, so there are mirrors that reflect the laser in the satellites. And there was even a pathfinder whose main mission was to try and see that we can really isolate. So it will be a free-falling object, despite being in a satellite in this constellation. So that was checked. That was launched in 2012, and it gave very good results. And the noise is based on that. So same thing, pretty much, and tested to an extent. Right, so moving onwards, there is one last future experiment that I would like to mention, which operates in a, well, significantly different way, in the sense that instead of shooting a laser between mirrors, this is a cold atom experiment. So the way it operates is it produces bunches of cold atoms, which are then launched along the baseline, and then come back down to have interferometric measurements performed on them. And then, of course, there is a laser going down, going through the baseline. So the atoms experience a momentum kick whenever the laser hits them. And then if the length of the tube would not change, we would see a very regular pattern of atoms in excited states coming from the hits that they get from the laser. If, however, the length does change, we will see something much less trivial, and that will allow us to tell that the length of the tube has changed. Right. So the reason I'm mentioning this is because, again, I was involved in two of those collaborations, so ION and EDGE. ION was a UK-based experiment, well, still is, which is actually right now, the first initial proposal was successful, and ION 10, the very first incarnation of this, which will be 10-meter tall, will be assembled in Oxford. This is a prototype device that we don't really expect to have very meaningful reach for actual sources of gravitational waves, but we can at least verify that we can measure its length. But there are many more experiments of this kind that are popping up in various places. For example, there's a sibling experiment to ION, which is called MAGIS, with pretty much the same setup. But this is more ahead. So MAGIS 10 was already done several years ago, and now they are working on a 100-meter version of the device. So this is, and there are many other MIGA and ZYGA, for example, projects that are trying to realize this same setup, or slightly modified setup, but still using cold atom technologies. So this is also moving forward. I should say that, again, the aim is to eventually realize a kilometer scale terrestrial device. And there is well, just earlier this year, there was a collaboration formed to try and realize that goal, to gather the smaller experiments and really try to cooperate between them to maybe produce something bigger. This has a terrible acronym because the name of the collaboration is Terrestrial Very Long Baseline Atom Interferometer. But it started proceeding already. And again, I am the representative from the University of Warsaw for that collaboration. So again, if you would like to join or would like to contribute something, please let me know. And again, I'll do what I can to help. And then I should also mention that eventually a very long-term goal would be to, again, launch that technology into space. So we did produce a proposal, which was called EDGE back in 2019, because that's when the European Space Agency had its big call for proposals that are supposed to be realized in the 2050s. And even though, well, so the results are already in, of course, there's no final decision being made so far, but at least the conclusion from that panel was that one of the 3 large-scale experiments is supposed to allow us to, well, improve our observations of the early universe. So it could end up still being EDGE, provided that the other experiments prove successful in the meantime. Okay. Okay, so with all this very optimistic prospects, maybe let me tell you a little bit about what's going on in terms of research concerning this, because this is, of course, not just well, digging appropriately big tube and installing devices. There's still a lot of theory to be done. And the one simple problem I would like to mention, but before that, let me tell you what the lines are on the plot. I've been putting some lines. I never said what they were. These were so-called power law integrated sensitivities. This example is for LISA. The actual detector sensitivity, so the instantaneous noise that it will see is the red line. And to construct, well, the power law integrated sensitivity is supposed to visualize the reach of the experiment. So the way we do it is we compute the signal to noise ratio, which can be significantly different because you see there is the time of operation, which is several years. So as long as we know what the noise of the detector is, we keep on taking data and building up, well, lowering the error so we can discover even weaker signals. Now, the way to construct this is just to produce a bunch of different power laws. Those are the blue lines that I'm showing here. So with different alphas. And then we choose the amplitude for each one such that the SNR is the threshold that we want. In this example, it is 10, such that it corresponds to a discovery. Then the power law integrated sensitivity is an overlay of all of those lines. And it has a very simple interpretation, which is that if a power law signal just touches it, it will be discovered because the signal to noise ratio will be 10. So this is, well, a simple way to visualize the reach. But this is, of course, not the whole story. There are still sources of noise that are not fully properly taken into account. So I have to take a step back and, well, maybe to confuse you a bit, this is a very similar plot to the previous one. These are instantaneous sensitivities of the same experiments, but I changed the variables to characteristic strain because this is the variable much more often used for astrophysical sources. And indeed, this plot is about astrophysical sources because each of those lines is a binary of black holes with a given mass at a given redshift. Now, the reason I'm showing you this is that we already know there is one population like this, the one we are observing in LIGO currently. And the point of this plot is to show you that this last part, this is the merger that we see, well, as a very bright event in LIGO. Well, it's just a part of the emission. In practice, the binary will keep on emitting gravitational waves as it in spirals, and the distance between the black holes shrinks due to emission of gravitational waves. And it will do so for a very long time. So these dots correspond to the time before collision. So 10 years, then 9 years of emitting. Later it will be here, and then you see how the time goes by. Eventually, well, LIGO currently mostly observes those final few moments of the binary. But this is important because, as you can imagine, LIGO is now observing quite a few of those binaries, and eventually it will be very difficult to tell them apart. So indeed, what we can do is integrate the signals from all of those binaries in a population, and what that will do is it will give us this gray line, gray dashed line here. This is the total well, one would say stochastic foreground that this population would produce. Now, the problem with that is, of course, if we have a stochastic foreground and a stochastic background, in a lot of ways they are identical. So what we will be observing is a sum of the two, which will, of course, make observations much more difficult. But this is not the end of the story. There are ways to mitigate the problem. And again, well, I will just use my paper from a few years ago as a very simple illustration, but there are a lot of people actively working on implementing those strategies, because essentially what one can do, this is the first and simplest idea, is that, well, as you know, LIGO is currently observing quite a few of those binaries, but it has not seen a stochastic foreground just yet, meaning that at least some of them we will be able to identify individually, and then once we know what their signal is, we can just subtract it from the data stream. So this is what this plot is illustrating. Essentially, all of the binaries that each of the experiments will see with a signal-to-noise ratio, which was taken to be 8 here, I believe, we simply took out of the integrand to see how the foreground will look once those are taken out. And these are the colorful lines you see. So for example, this is how this foreground will change for the Einstein telescope. So we can see it can subtract quite a lot of those binaries and improve its sensitivity quite a bit. The problem is, for example, with LISA, because here, as I told you, those binaries are very early in the revolution. So there are very faint sources that, well, point sources in the sky that emit for a very long time, but are relatively weak. And so they are very difficult to individually observe, unlike the final very loud moments of collision. So LISA will not be able to identify that many of them. And so the line for LISA is pretty much the same as the total foreground. This is, of course, not the end of the story. There are other ways to go around it, but this is just to illustrate what sort of problems one is facing when thinking about those detections. Maybe let me skip this and just tell you a few words about the developments that are going on. There are some public codes that are aiming at trying to reconstruct the stochastic background being produced. But, well, more importantly, at least from my point of view, there's the stochastic gravitational wave binner code, which is produced by the LISA consortium. And indeed, last year, there was a significant update. There were 3 papers concerning reconstruction of sources, well, reconstruction of signals from phase transitions, cosmic strings, and inflation. And the ones that I highlighted, well, I highlighted because I was involved in those projects. Right, so this is, well, there's still a lot to do, but there is a lot of people working on this currently. And this finally brings us to pulsar timing arrays. So let me in a very trivial way, try to explain to you what pulsar timing arrays do. Of course, pulsars are neutron stars that beam energy out of their poles. And so through their precession, sometimes they beam towards us. So for us, this is a blinking source in the sky, which, because those are very massive objects, it turns out they are extremely reliable and very stable. So in fact, well, we can use the Doppler shift of the signal when the frequency of emitted pulses changes to try and tell what the distance between us and the pulsar has changed. So this is in the simplest way how the simplest explanation of how a pulsar timing array operates. It simply times the arrival of pulsars, and then there is a big problem with data analysis because one needs to really disentangle this time stream of data into possible information of gravitational waves. Now, of course, you can imagine there are a lot of things that can cause a pulsar to move. So but there is something special about gravitational waves, which is, of course, well, their nature. For example, in a very simple, just to illustrate this, if a plus polarization gravitational wave would be going through the blackboard, the pulsars would be moving in a correlated manner, something like this. Of course, for a stochastic background, you need to do two integrals of that, but it turns out that this pattern perseveres, and in the end, you expect, if the movement is due to gravitational waves, see a correlation between the pairs of pulsars depending on their separation in the sky. So if this pattern is proved, we will know that the source behind this was gravitational waves. And indeed, so those are results from the 4 collaborations that put together their results and published them all together, well, previous summer. These violins give us an idea of the distribution of probability. So we can already see that it's not completely trivial to, for example, draw a straight line, or at least it will be a much worse fit to the data than the Helms-Dons curve, which would correspond to gravitational waves. It's a bit hard to quantify, but I think at least for the nanograph data, which is in a way the most constraining, the significance is roughly 3 sigma. And what is important is that with every subsequent data release, the significance is growing. So it seems like there really might be a signal behind it. Now, of course, there are many possible interpretations. The errors are still relatively big. The very generic explanation for this signal would be supermassive black hole binaries. Of course, they have the advantage that we know supermassive black holes exist. They are, for example, at centers of large galaxies. But astrophysical models have a hard time predicting the rate at which they would collide. So it's very unclear. I mean, the predictions from astrophysics always gave a very big range of the possibilities of the amplitude for this spectrum. But as I said, there are a lot more possible sources, for example, cosmological ones. And this is what I would like to switch to now. And again, I'm highlighting, there were quite a few papers, including collaborations, one that talk about this. I will focus on the one that I was involved in again. Right. Maybe I will skip this, but I'll try to explain to you very briefly what that was supposed to tell you. So this is the final result of that check of what source gives the best fit to the data, multimodal analysis. And there are quite a few scenarios that we took into account. Perhaps I should say what this delta big is, well, Bayesian information criterion. So essentially, this is the likelihood, similar role to chi-squared. But then we have plus k, so this is the number of parameters for a model, times the logarithm of the number of measurements, and we have 14 frequency bins, so this is a logarithm of 14, and k depends on how many free parameters each model has.
Did I understand correctly that these measurements of the pulsars were not made, or they already made?
They have been already made. There is data available. Everyone can access it.
Big sources of gravitational wave available there, right?
Yes, exactly. Yes. Yes, in fact, what we are using is the nanograph data only. They made their, well, it's the most constraining one, and also they made it the easiest to access. And it's very non-trivial to combine different data sets, so we just used the one. Right, so Bayesian information criterion. So this is, of course, this feature here is to penalize model that fit better just because they have more parameters, so it's easier. And then, of course, this is, well, the bigger the number, the worse it is, the worse the fit was. So first, gravitational wave-driven supermassive black hole binaries. If we assume supermassive black hole binaries only lose energy due to emission of gravitational waves, we would have an f⁴, a very simple signal, just two parameters that just one parameter that controls the amplitude, and it's not a very good fit anymore. So there is this is delta compared to the baseline, which will be the second model. So this is already, well, not the best fit.
For these events, so I mean, how far the sources are in these particular cases. So if I have supermassive black hole binaries, I would believe that they are very far away, right? Because you need essentially two galaxies.
Definitely, yes. They would be very far, but it's not, well, so what we are seeing now is a sum of a lot of those sources, and it's really difficult. So maybe I will go back here for a second. Well, it's really non-trivial because I don't think, so none of the events was identified individually. I should start with that. In fact, we cannot even tell, well, there will be ways to tell if the source is astrophysical or cosmological, but the data is not of quality that would be required to do that yet. Essentially, we don't even see anisotropy so far. Okay, maybe this plot isn't very helpful. We don't even see anisotropy, so it can be an isotropic background, meaning that if we don't see a single event, we definitely cannot disentangle the distance from a given source. Although it is true that there would be relatively few sources. So maybe I can go back to this. That's why, well, the signal from those binaries was, well, at least in this paper, shown as a probability distribution, because there are few enough sources that it doesn't really come up to being very, well, continuous line, but instead it will be jagged depending on how many sources there are in each bin of frequency. So this is why it was plotted as, well, probability distribution, depending on the parameters of the population. But again, each realization will be slightly different. But what I wanted to say is, right, so the second possible model, gravitational waves plus environmental-driven supermassive black hole binaries. So there is essentially an extra mechanism of energy loss that makes the supermassive black holes coalesce faster. And we just used a simple model that I briefly showed in the previous slide, which has some phenomenological parameters that don't really tell us anything. I don't think anyone knows what those parameters should be, but it does give a best fit, which is, well, this number here. And we always compare the other possible sources to that number. Well, and as you see, all of the possible cosmological sources, at least for now, give us slightly better fit. So cosmic superstrings, phase transitions, domain walls, scalar-induced gravitational waves, first-order gravitational waves from inflation, and even audible axions. They all fit slightly better, but of course you can also see that the number, well, the difference between the numbers is small, meaning that the difference is less than 2 sigma. There is, of course, nothing indicative of this just yet. But I'm particularly happy that the signal from phase transitions is one of the best fits, because this is what I will continue to talk about in the remainder of the talk. And this is because this is the one spectrum that, well, we actually computed, while the other ones were taken from the literature. Okay, so this is a plot of the best fits. Again, you see that, oh, this is very poorly visible, I'm sorry. So there are gray violins that you cannot see, which show the data. And then there are yellow violins, which show the, well, possible realization of supermassive black hole contribution. And then there are the best fits from all the models. Maybe this doesn't really tell us very much, but there is one point that I wanted to make, which is that sadly, with exceptions, which are, of course, supermassive black holes, which we would see collide somewhere in the LISA frequency band, and cosmic superstrings that would produce a very broad spectrum, most of those sources will not really be observed by other experiments, meaning that it might end up, well, we might end up in a situation where it's really the shape of the spectrum that we'll eventually have to use to tell apart which source it really was. So this is why, well, computation or having an accurate spectrum for each of those sources is relatively important, or might prove to be important in the future if this proves to be a signal of cosmological origin. Okay, so on to phase transitions. So of course, the starting point is the standard model. I will not say much about it, but I will say that it's based, as you know, on the symmetry group SU3 cross SU2 cross U1. The only reason I'm mentioning is to say that it is based on spontaneous symmetry breaking. So of course, this SU2 cross U1 is broken into electromagnetic U1, and this is how particles gain their masses. So phase transitions are something which is very common in particle physics models. This is not just something that I focus on. It's really there, although I am focusing on a particular type. And to try and explain what this type is, let's just look at the world's simplest potential. So we just have a scalar field. And what we compute is the thermal corrections to the potential, which in high temperature approximation, this is again the simplest thing one can do. They always take the form in which we have the coupling T squared phi squared. This already tells us a lot. So we know that in the early universe, the temperature is very high, meaning that at high enough temperature, the potential will look like this. And this is the global minimum of the potential then. So initially, the field will be in this symmetric phase. Then as the temperature drops, another minimum develops. And I'll be interested in first order phase transitions, meaning that I would like for this other minimum to develop in such a way that there is a significant barrier between the two. Because what we end up with then is that when the temperature drops even more, the field is still trapped in the initial symmetric configuration, but it will eventually penetrate the barrier and occupy the deeper minimum. Sadly, I have to mention that it doesn't work like this in the standard model. In the standard model, this barrier is very small, and unfortunately, none of these interesting things would happen. But as you know, the standard model lacks several things that cosmology would require. And actually, well, realizing them, yes. Yes, of course.
Because this looks very much like the old inflation model of proofs, right? Which is kind of incompatible with observation because of the bubbles that will collide with the sun. So there are different phases. So is it obvious that this model is actually compatible with cosmological observations, and there are no, this bubble collisions and stuff?
There are bubble collisions, but this is very good. I will talk about this precisely. But the confusion. That depends on the model. This will be a free parameter for us later on. So I will come back to this. But to explain the difference in the old inflation picture, the problem was that there was no temperature dependence because you had a very long period of inflation. So indeed, if the decay rate doesn't change, there is no percolation. We know this. But if there is a temperature dependence, there is a large part of the parameter space in which this works perfectly fine. Although there will be some inflation, but not a lot. Well, I'll continue and show you what I mean. Right. So coming back. Right. As I said, well, what we want to compute is when the field eventually penetrates the barrier and ends up in the deeper minimum. And to do that, what we really do is just try to find solutions for the field's equation of motion, which correspond to that process taking place. In most models, and this is what I assumed in this equation here, the way this happens is through thermally induced excitations of the field. So this is in thermal equilibrium. I drop the time derivative. This is independent of time. And the second thing, I need the solution which has the smallest action, meaning I'm taking the most symmetric one. And that, of course, means I'm just talking about spheres. So those are spherically symmetric configurations. This R is the normal radius in 3 dimensions. Then this is the equation that I'm dealing with. And of course, there are appropriate boundary conditions. So first, the derivative at 0 has to be 0 just for this term not to be spurious. And secondly, I want a configuration in which something interesting happens at the origin of the coordinates, but far from the origin, the field has to still be in the C of this initial configuration before the transition takes place. Then, of course, what I would want to do is compute the action associated with each of those solutions, and then I will be able to tell that nucleation started taking place if this decay rate compared to the 4th power of the Hubble rate is, say, of order of 1. This is, of course, exponentially suppressed, so this calculation, well, is very important. Now, what we will use later on is that those solutions always end up looking roughly like this. So close to the origin, the field is already beyond the barrier at some larger value of the field. Then there is a wall, and of course, far from the origin. As I said, this is just, well, its solution is in the C of the initial symmetric phase. So that, of course, corresponds to simply, so this is just a bubble in which the symmetry is broken in the C of false vacuum. Again, at the time when this decay rate is close to the Hubble rate, we will see that those bubbles begin to nucleate, after which they will continue to expand, eventually collide, and then we'll end up in the situation we want, which is we'll end up in the broken phase. And there are a few parameters that describe this process. First one is the strength of, so-called strength of the transition. This is the difference between the minima of the potential. So essentially the density of vacuum energy at the time of the transition over the, well, previously existing radiation density background. So this is the first key parameter. Of course, this effectively tells us what part of the total energy takes part in the transition, because this, well, this is just delta V. The second one is the characteristic scale. So again, due to this exponential dependence on the action, we can change the variables and ask how this would look in time. This gives us this inverse time scale beta, which is another key parameter. As you see, just taking a derivative of this, I can describe it as a, well, a derivative with respect to temperature of the action. But maybe to better explain what this does is I will tell you that if we compute the average radius of a bubble at the time of collision, just assuming they nucleate with this rate given by this, we will find that the average radius will be this. So essentially it's 1 over beta. The average radius is our star. And then we, well, I should say, compare it. This is r star over 1 over h. So we're comparing the size of a bubble to the size of the horizon at the time. And then there is only one very simple geometric factor that is connecting the two parameters. So this is the scale that will really play a role in the results. And this is why. Okay. So.
But I'm worrying, this model isn't, because it probably, well, naively speaking, it has a huge cosmological constant before the phase transition, right?
It does.
And then isn't that compatible with observation? Because it's going to be of, well, order of GeV cosmological constant, right?
Oh, but it disappears after the transition.
That's right. But before the transition, the universe is basically in the second phase, right?
It is. It's inflating, yes. But, well, no, I think there is nothing preventing this.
Inflation at
yes.
model scale, right? So there are two stages of inflation, right?
Yes, there is a, sometimes this is called thermal inflation. Yes, exactly. Exactly. So indeed, well, this never happens in practice, but what one should take care that the number of e-folds of this secondary inflation phase isn't too long, because then we would end up in trouble with observational constraints on inflation. Okay, so very quickly, So I will specify that I will only be looking at very strong phase transitions. The reason for that is that generically, very generically speaking, the spectrum scales, this is the amplitude of the spectrum. It would scale like this. This is alpha over alpha plus 1, well, to power 2, but essentially this is the abundance of the source. So this is you will see this in the literature, but this is essentially rewriting vacuum energy over the total. So this is what, of course, controls the amplitude. And the other thing is, of course, the appropriate scale, also power 2. But for us, well, you will see this later on when we are doing the fits. But the model that we want to really satisfy the data that we get from pulsar timing arrays has a huge amplitude, which is very difficult to achieve. So we will only focus on models where this alpha is very big. So indeed, we have a relatively long period of this secondary thermal inflation. Because that will maximize the signal, then essentially, well, the abundance of the source is 1, roughly. And then the other variable left in the game is, of course, the length scale of the transition. And the other important one will be the temperature to which we reheat after this transition. So the temperature will only be, of course, given by the energy scale, because we're, well, previously existing radiation is completely negligible, and the one that we will see later on is only coming from converting the vacuum energy into radiation in the process of the transition. Okay. So now, well, I'll try to convince you that this is, in particular, this setup of extremely strong transition can be described by bubbles, which are, well, approximated as just spheres with some energy density on them. This is a very trivial plot, but this is supposed to show you, and indeed probably does, show you how we compute the gravitational wave spectrum, which is, we have a 3D box, we perform a simulation in which those bubbles nucleate and grow, and as long as we know what is the energy at on each of those spheres, well, we just compute the required integrals and we end up with the final spectrum. So this is a complicated process in terms of, well, the technical part, but it's not conceptually complicated at all, as long as we know how the energy evolves on those spheres. So this is what the rest of this derivation will be about. Essentially, what occurs in a transition like this is a lattice simulation of a scalar field. The color is, this is just the energy density, the logarithm of the energy density. So initially we have two bubbles nucleating. This is, of course, a cut so I'm showing it in a 2D plane. We have two bubbles nucleating. I don't know how obvious this is. Maybe the wall was initially a bit too thin, but what happens in this transition is that the bubble grows, and it's converting this vacuum energy outside into more energy on the wall. Essentially, this is what this process does. And then, of course, at some point, these more and more energetic walls will collide. So back in the day, so this has been known since the 90s, but initially people always used the so-called envelope approximation, in which we assume that when the walls collide, they just disappear, which is the first thing you would think of if you don't really want to do the simulation. But of course, it turns out in practice that sadly, this is not really the case. The energy will keep on propagating in terms of gradients of the field. And then, of course, it will dissipate because there is no more driving force. So the bigger the radius after the collision, the less energy there will be. But it turns out that this remainder is very important for the shape of the spectrum. Right. So we will use that. Maybe I won't get into this too much. This is not absolutely crucial, but I will just tell you that, of course, the way to try and find what this energy density is to, again, run a simulation. So this is a cut through a simulation where two bubbles nucleate. This is time. And we see that the bubbles collide at this point. And then what we're interested in is how the energy scales on this line where the wall would have been had there not been a collision. And what we find is that for models of interest, so gauge symmetry breaking, turns out that this energy is just r to power minus 3. So it scales in a relatively simple way. Now, another less trivial fact, maybe I won't do a very good job of explaining this. This would take a whole other seminar, and I have 0 minutes, according to my estimate. But essentially, if the source is instead plasma, because this is something which happens very often in those transitions, that even though the plasma is very diluted, it still will produce a force on the wall, slowing it down. So what we will end up with is the energy going into a heated fluid shell instead of the wall itself. But what I'm trying to show here is that if the strength of the transition is larger, then this profile is more peaked. This is the kinetic energy of the plasma. But before I lose you, let me just say that it happens so that it scales in the exact same way. So this is a simulation of what this heated fluid shell will do after the collision had transpired for a very energetic transition. This is again the kinetic energy of the fluid shell. And as you see, it happens, well, this is time goes by. This is our heated fluid shell. It loses energy at the rate of r to power minus 3. So we are very happy to say that both those sources actually look in the exact same way in the end. Or, well, at least approximately the same way, which allows us to already compute the spectrum. Again, when you create bubbles in a box, we know how the energy scales. We end up with this maybe non-super trivial looking fit, but this is relatively simple. We just have slope on the left-hand side, which is A, right-hand side slope B. C is a parameter controlling how flat the top is, and A is the overall amplitude of the spectrum. Well, but in the gauged bubbles case or fluid case, as you see, the numbers are relatively the same. C is the only problematic one, which can, well, it's reconstructed relatively poorly, but other than that, the spectrum is essentially symmetric, and both slopes happen to be 2.4. So we know how the spectrum looks like, and then of course we can just try and fit it to the data using the scaling from several slides before with the parameters. Again, the two parameters in the game are temperature and this appropriate length scale. And this is what I meant saying that this transition has to be pretty much as strong as it can be. So beta over h, maybe this is not completely trivial, but there is a lower limit on it. And this is exactly coming from this thermal inflation problem. If beta is smaller than 4, we end up running into problems with percolations. So then it's hard to break this exponential expansion of the false vacuum, and we will have isolated bubbles that never meet. This happens roughly when beta over h is equal to 4. There's another problem, which around that time we start producing black holes, probably, but I won't get into that right now. The point is that there are definitely bounds on this, and as you see, our fit only works very close to those bounds. So the transition is indeed as strong as it can be, or the bubbles are as large, as energetic as they possibly can be without running into obvious problems. So this is the first result. The second one, you see that the temperature is relatively low. This is just 1 GeV, which can indeed lead to problems. Specifically, as I said, this isn't just the standard model. We definitely need new fields. And they would, well, then they would have to predict transitions at an energy of 1 GeV, which is definitely probed by the colliders that we already have. So it's not completely trivial to produce a model which does this. One would need to hide it from experimental signals. But I can tell you that people have, for reasons that I don't fully understand, there was a flurry of papers at the beginning of this year, and now there are at least 7 models that do it. So people have started on it, working on it, I think, as soon as the news broke, summer last year. And now there are quite a lot of models that try to evade constraints from colliders. What we were doing in the meantime was just trying to look at dynamics of the transition, not really looking into how to hide this phi field, which is again a new field that we add from the interactions with the standard model fields, but rather just looking well, at the possible parameters that we can obtain. Well, and just to very briefly show you towards the very end, this is of course doable with a potential like this, which is a classically scale invariant one, meaning that the mass term is only coming from this thermal correction. If we have a model like this, then this gauge coupling is here. This is the VEV of the field. And as you see, there is a large part of the parameter space where we can indeed obtain, for example, beta equal to 4. This is, everything is fine. It's not super fine-tuned. If we change the parameters, beta changes relatively slowly. Of course, it increases. And here, this is the part where we run into problems with percolation. And then the very last bit, of course, we can fit the nanograph data in this simple model. We already knew as much. The interesting thing is that other gravitational wave experiments will also be great probes of this, as you see. So for example, this is the reach of LISA, then somewhere here. But essentially, you see that the entire parameter space up to where I cut the plot will be in the reach of future experiments. Which brings me to my conclusion, which first, well, gravitational wave experiments give us unprecedented access to fundamental physics models. We just saw this. The second one would be that the gravitational wave spectrum from strong transitions is the same regardless of the, well, very intricate dynamics of the source, provided that the phase transition is strong, we find the same spectrum. And finally, of course, a strong phase transition is one of the best explanations for the current Pulsar Timing Array data. And that's all that I had for you. Thank you.
In the LIGO detector, are we going to have just a single interferometry experiment or a few of them, like we have in the terrestrial experiment?
So this is non-trivial, but a triangle like this can be expressed as two different independent interferometers, approximately. So in practice, there are two, and there is a null channel which allows us to, well, probe the noise. So in principle, it works in the exact same way as two different interferometers. You mean in this plot? What is the minimum of the additional gradient? Ah, yes. So no, this is not, well, I misspoke, I'm afraid. What I meant to say was that you see in the envelope approximation, what it tells you is that the walls disappear on collision, but in practice, you see the energy propagating forward, and this energy is in the form of gradients of the field. So if you just do a simulation with just the scalar field, it will be a wiggle in the field moving forward. And that's what these colorful lines here correspond to.
From other terms that you know, from gravitational waves, or also mean observatory example.
Yes, so there are some projects that I've been talking to about with Professor Bulik, for example. There are some projects which, again, well, they mostly focus on this detection part. So trying to take into account the binaries that will be a problem. So there are some projects. They are now waiting for a talented student to take them on. But we are also in contact in general concerning, let's say, the Polish contributions to all of those various experiments. So yes, there is quite a bit of collaboration.
Bardzo dziękuję, bardzo to było ładne.